First of all, I'd like to thank Tom Dykstra for inviting me. It is really an honor to be here. And yesterday, Dr. Ulrey spoke briefly about being out of the box. I'd like to think of it more as multi-dimensional thinking. You have a tunnel, and we have all the information around the tunnel. So we gather the information to solve a problem. And that's what we're going to do here this morning. During the winters, 2009 through about 2011, all kinds of snowfall records broken across the United States. This past winter, records broken in Alaska, Russia, record cold. Meanwhile, United States, very, very warm. Global warming is real. It's definitely real. What we have is a fight between two systems, global cooling and global warming. Just like in the spring when we have tornadoes, a fight between winter weather and summer weather. Which one's going to take over? And we're having a fight on that now. We've had global warming, now which one's going to take over? This graphic is from 1870 up to present time, showing the increase of carbon dioxide. There's no question about it. It's increased from about 270 parts per million back in 1870 up to about 395 parts per million now. This is a graphic, United States temperatures from 1880 to present time. This is present time right here. And the orange line, yellow line, notes the increase in carbon dioxide during this 110, 20-year period. From 1880 to 1930, you can see kind of 10-year ups and downs in the temperature, but overall, temperature remained the same. Then we had a 10-year spike in the temperatures. Then a 50-year downturn. And now we just had a 10-year spike again in temperatures. This is the typical global warming cycle. 2 10-year peaks in temperatures with about 50 years of cooler weather in between. And no relationship at all to increase in carbon dioxide. Carbon dioxide is a byproduct of global warming. Again, this is a graphic. This is the 2 10-year peaks that I just showed you. Global warming comes about every 230 years. This is back in the 1800s, 1500s, 1300s, 1100s, and back around 900 AD. They all have a signature of the twin 10-year spikes in temperature. Well, us humans, we need an afternoon nap sometimes to get us through the rest of the day. We get a little sluggish. And this is what happens in the global warming cooling cycles that come every 230 years. During global cooling cycle, the Earth needs a little nap to regenerate. During the longer cycles that come every 120,000 years, Earth needs a longer nap to regenerate. What we have are about 30, 40,000 years of a glacial period to give the Earth a good long rest. And then the warm dynamic periods such as what we're in right now, peaking out. Back in May of last year, a year ago, there was a person that said, oh, world's coming to an end. Meanwhile, over on the right, we had people talking about global warming. Earth is coming to an end if we don't do something. Well, science said in the 1400s, world is flat. We know what happened there. 1970s, Earth is entering ice age. That didn't happen. 2004 and 5, after the big hurricanes in Florida, anthropogenic, man-made global warming is causing stronger hurricanes. I researched the cycles. National Hurricane Center researched the cycles. It's not true. We had just as strong hurricanes in the past. 2004 to present, people saying Mississippi River flood last year was caused by global warming. And tornadoes last year. I've researched this. I track them on my model. This is all cyclical. And now, 1990s to present, Global warming caused by man. The rest of this wasn't right. What do we think about this? Since 1995, we've had manipulation by the university grant system. Grants to universities were only granted to study man's connection to global warming. You couldn't get a research grant in Europe, the United States, to study natural cycles. Because of this, the journals, anything printed in the journals was the man-made global warming. So when it was printed in the journals, the media would get a hold of that information. This is what we'd see in the media, man-made global warming. So the media would hype it up. That would hype up the government. The government would put out more grants. They're all hyped up. Now, there was a poll out a year ago that 90% of the grant scientists, ones receiving grants for studies, believe in man-made global warming. 85% of the general meteorologists and climatologists say it's mostly natural cycles. Meanwhile, this trickles down to the energy community, where they have to become politically correct. Let's take a look at the Earth's atmospheric gases. 99% of the atmospheric gases are made up of nitrogen, oxygen, and argon. Leaves 1% for the greenhouse gas. Of the 1%, almost the entire 1% is water vapor. Carbon dioxide, can't even see it on my graphic. So let's blow it up. Here we are, greenhouse gases, 96%. Carbon dioxide varies between, we'll go to parts per million on it, so it's bigger numbers. Goes between 160 parts per million to 400 parts per million, compared to 10,000 parts per million for water vapor. Now in water vapor, as I said, it varies between 160 up to about 400 parts per million. Scientists say we've never been above 300 parts per million over the past couple million years. I'm going to show you that we're frequently up to 334 parts per million and even up to close to 400 parts per million. Now, is the higher levels harmful? Greenhouses, they keep their carbon dioxide between 500 to 1,000 parts per million. Beneficial for plant growth. When the dinosaurs roamed, carbon dioxide levels were 1,000 to 1,500 parts per million. Plants and animals, big and robust. Oxygen back then was 31%. We're down to 21% now. 21%. That's because of the lack of carbon dioxide. So where does carbon dioxide come from? Carbon dioxide cycle. On the bottom of the picture, it's from dead organisms, fossils, fossil fuels, decaying plants, root respiration, animal respiration. And that all goes up into the atmosphere. And even the oceans will either take it in or put it out. Over on the left, you have a tree. Trees take in carbon dioxide to balance it off. But if it was only that simple, we have to deal with interglacial warm periods every 116,000 years that cause a change, global warming cycles every 230 years, and changes in seasons, winter to summer. They all have changes in carbon dioxide. Just 15,000 years ago, up over New England, from almost New York City northward, it was in a glacial period. Mile-thick ice year-round up in New England still. And of course, because of that, you didn't have any bare ground from there northward, so you didn't have the natural feedback of carbon dioxide into the atmosphere. Then the glacial period went away. Well, this is what it does to the carbon dioxide cycle. You get the ice age. All your feedback of carbon dioxide goes away. You have a big negative loss in the atmosphere. Colder oceans absorb the carbon dioxide, store it up for 30, 40,000 years, waiting for the next interglacial period that comes every 120,000 years. Photosynthesis drops by 50 to 75%. When the ice age goes away, all the feedback comes back. The oceans dump all that carbon dioxide back into the atmosphere over a matter of only about 10,000 years. So we have a huge increase in the atmosphere. Photosynthesis rises by 50 to 75%. And this is what it looks like in the long term. On the left, red is temperature. This is back 430,000 years ago. Blue is carbon dioxide. Every 120,000 years, we have the interglacial peak in temperature in carbon dioxide. And during the past 40, 50,000 years, this was our very deep glacial period that we just came out of. How can we get past history to produce a map, a graphic that I just showed you? Well, my grandchildren say, I'm Santa Claus, so of course I'm in my backyard with my thermometer and I'm taking the records the past 500,000 years. Or we can go down to the Antarctica. What we have here is a block of ice. In the ice, you see air bubbles. In the air bubbles is trapped atmosphere. So if we can find some old ice, extract the old atmosphere, we can determine how much carbon dioxide there was in the air at a given time in history. So the Russians went down to the Antarctica, subglacial Lake Vostok. Very thick ice, water down on the bottom of the lake. They drilled down about 13,000 feet. That's a lot of ice. That is called old ice. Ice at the bottom, 430,000 years old. Up at the top, the first 7,000 years of the ice core is called new ice. You cannot use the new ice because it takes 5 to 6, 7,000 years for the air bubbles to become permanently locked in the ice. Up until that time, it moves around in the ice. So you can't use new ice. That's what an ice core looks like. They take off a piece of ice to analyze it, and this is the graphic we get. On the left, 338,000 years ago, took 50 global warming cycles over the course of 10,000 years to peak out. Each global warming cycle, you get warmer and warmer, carbon dioxide increases. However, science has found there's a lag in the increase of carbon dioxide by 200 to 800 years. Temperature goes up first, not carbon dioxide. When it peaks out, the peak of 298 parts per million for carbon dioxide was several thousand years after the peak of the temperatures. And then you can see the temperatures falling like a rock for several thousand years, but carbon dioxide remaining high. If carbon dioxide causes temperatures to rise, we would have had runaway global warming back at that time. Temperatures could not have fallen. And the carbon dioxide levels were higher than 298 parts per million. The plot is about a 200 to 1,000 year mean. And you know when you take a mean, you have spikes way above it. And this is why they say we've never been above 300 parts per million, because it's a mean value over 200 to 1,000 years. The next cycle took 30 global warming cycles. There's 50, there's 30 global warming cycles. Next one took 40. One we're in now, there's only 20 global warming cycles up until about 8,000 years ago when we had 260 parts per million. But we do know that the temperatures were very high at that time. That was the peak of our interglacial period for temperatures, because 7,000 years ago there was 50% less ice in the Arctic than there is today. 50% less. But as you can see, we have been missing carbon dioxide here because it's the 7,000 year period where we cannot acquire the carbon dioxide from the ice core. So let's acquire it ourselves. We're going to take a look at the cycles again, and what we want to do is look to see how much the carbon dioxide rose during the last 4,000 years of a cycle. In the first cycle, back 338,000 years ago, it rose 57 parts per million. The next cycle, it went up 50 parts per million. The next cycle, 67 parts per million. Then let's take a mean of that. The mean of the rises are 58. Well, back 7,000 years ago, we were 260 parts per million, but we had 20 more global warming cycles to go yet. So let's add that mean to it. Comes up to 318 parts per million. That's what our mean value should be right now, above 300 parts per million. Now, the scientists will say, yeah, but we're up to 370 parts per million on the ground surface down at Lake Vostok, way up high. But that's an instantaneous reading from an instrument, not a mean. They don't tell you that. It's an instantaneous reading. So we won't take a 1,000-year mean here. What we'll do is take a 100-year mean. What the carbon dioxide was 100 years ago, 120 years ago, and we'll mean that in, and it brings it down to a 315 parts per million for mean, just like my 318. We're exactly where we're supposed to be for carbon dioxide. There's nothing wrong. It's a natural cycle. Now, this is graphics created by Peter Tans, who will be speaking after me, called the carbon tracker. Carbon dioxide satellite information in the troposphere of the atmosphere. This is at the end of winter in 2009. Red is showing very high levels of carbon dioxide in the atmosphere, 393 parts per million, very high. Only 6 months later, it drops 15 parts per million in 6 months. The reason why is during the winter, you have a lack of photosynthesis. The plants are not taking carbon dioxide out of the air, so it's building up in the air. At the end of summer, the plants have extracted carbon dioxide from the air, so you drop 15 parts per million. Now, if you can drop 15 parts per million in just 6 months, what do you think you can do in 100 years? Photosynthesis. Okay, this is a study done by Dr. Beck. This is a leaf, plant leaflet. In the leaf, you have little cells called stomata. It's like our lungs. Excuse me, it's like our lungs, little stomata cells. They found an inverse proportion. If you have more stomata cells, you have less carbon dioxide, and vice versa. If you have less stomata cells, you have more carbon dioxide. And the beauty of this is a leaf lives 1 year. So instead of a 1,000-year mean, you can get a 1-year reading. And this is what he came up with. Down at the bottom, that's the 5 global warming cycles during the past 1,200 years. First global warming cycle back around 900 AD, plant stomata show that we're up at 400 parts per million, way back 1,200 years ago. Then in the course of only about 50, 75 years, it dropped down to 250 parts per million during global cooling. Next global warming cycle, peaked out again. Next global warming cycle, next global warming cycle, next global warming cycle. And then in 1860, 1870, instruments said we were at 260 parts per million. Plant stomata said 260 parts per million. Ice cores said 260 parts per million. All agreed. And then now, 375 to 395 parts per million, they all agree again. So plant stomata can be used over time. The beauty of it is it goes with the global warming cycles. The 1,000-year mean of the plant stomata is about 305 parts per million, just like our 1,000-year mean. It's exactly what we're seeing happen. We have rapid changes in just 75 years. This is my favorite part now. Earth's climate pulse, the cause. The orbit of the Earth, elliptical around the sun. Every 120,000 years, the moon moves out further from the sun, causes the 120,000-year glacial period. Then it comes in, swings in close, the 120,000-year warm period that we're in now. This is the Milankovitch cycles, very famous cycles, very well known in science. What I inject into it is the lunar solar precession. I add the gravitational cycles of the moon and the sun. If it was not for the gravitational tidal forces of the moon and sun, the Earth would spin out of control. What we're going to look at is the gravitational cycles, and especially the 9-year, 72-year, and 230-year cycles. Elliptical path, orbit of the moon around the Earth. Every 6 months, swings in close to the Earth. This is a perigee, proxygee, and in alignment with the sun. Perigee, proxygee, syzygy. Gravitational tidal force on the Earth increases up to 47%. That's a huge increase, 47%. So you would expect something to happen. And also, there's a position of the moon in the sky. That strong 6-month cycle I'm talking about, it'll start out in the northern hemisphere up around 28 degrees. Over the course of time, it takes 4 years to go down to the southern hemisphere, then back to the northern hemisphere. That's a 9-year cycle from the north back to the north. 9-year cycle of the gravitational cycle. What this does, between the new moon and full moon, great torque on the Earth, causing a plunger effect, gravitational pull on the ocean's atmosphere and inner core, outer core of the Earth. This is what the cycle looks like, the 9-year cycles. This is actual cycles, 1990, in the northern hemisphere, high in the sky in the northern hemisphere. 9 years later, goes from down to the southern hemisphere, back to northern hemisphere, and northern hemisphere. 9-year cycles. You probably recall, I showed you this earlier, temperatures in the United States since 1880, and I was talking about a 10-year blip in the temperatures. Well, let's put it in there. 9 to 10-year blips, just like the 9-year cycle. Now, this is some information that came out in American Meteorological Society Bulletin of last year, not my research. It was in the North Atlantic. What happens every so often is a pool of warm water pulses into the Arctic Ocean. Then it takes, this is the North Atlantic, Scandinavia, Russia, Alaska, Canada, and Greenland. So it pulses in, takes 13 years to go around the Arctic. So what I did, I want to take a look at this on my cycles. They've researched 3 cycles. This is where they showed up on my cycles. Right at the peak of the northern hemisphere warm pulse. The first pulse, 1990, came in, warm pulse of water, went in the Arctic. That's when the ice started to melt up in the Arctic. The ice melts from the bottom up. It's all floating ice. Remember, what, some 80% of the ice is below water? Melts from the bottom up. The pulse in 1990 was warm. 2008 was warm. One in 1999, the middle pulse was very warm. That's what's caused the great melting up there from 1999 up to about 2008. And that's a signature of the global warming cycles, that very warm pulse that comes in and we see our 10-year peak in temperatures. So this is what happened. 1990, the first pulse came up around, took 13 years to go up around the Arctic. Then the warmest pulse came up around and did all the melting. 13 years before it gets diluted. And another one just opened, went into the Arctic in 2008, a warm pulse, not as warm. It's going to take 13 years. It'll be 2021, it'll be completely gone. 2021, actually be pretty much gone maybe by 2018. So now let's put it all together on just a couple last slides here. What we have here, this is the global warming, the temperatures, Earth's temperatures. You know to recall the global warming cycles. This is the running mean value of the Lunisolar precession. Let's see what happens. When the moon lowers in the sky, gets down to the bottom of the cycle, in 2075, the first 10-year spike in global warming. Over on the right of the cycle, second spike in 1315. You come off the lunar cycle, And look, the temperatures drop like a rock. Global cooling, drastic global cooling. Next cycle, the moon comes down, bottom of the cycle. First peak in global warming, the second peak in global warming. We come off the cycle, drastic global cooling for the next 100 years. 1775, come down, global warming. 1800, comes off global warming, drastic cooling. And I'm going to talk about this yellow dot here on the next cycle, the year of no summer, on the next graphic. Then, our current cycle, 1930, our 10-year pulse in temperatures, 10-year pulse. 2008, we're coming off the Lunisolar precession cycle. We're going to be heading very soon into drastic global cooling. My final slide. Change on this is, I plotted the VEI, which is the Volcanic Explosivity Index for volcanoes. Goes up to 7. So I plotted 5, 6, and 7, the strongest volcanoes. The yellow ones, yellow dots, would be the VEI 5. The white is 6 and 7. And kind of what you see is, back up here, you don't really see much except there's more in the past 400 or 500 years. And some of that's because observations are better. We have more people on Earth and we know the power of what happened. But what we want to do is take a closer look at this. We want to see what happens about the first 20 years of the drastic global cooling when you head into global cooling. So we're going to box this off when we go into global cooling. Now, the rest of the volcanoes are more in the deep part of the global cooling. But we want to look at the first 20 years, see what's going on, because we're coming up to that. So what we're going to do is box off the ones we don't want and take them out of there. Now we're at the global cooling cycles and what happens the first 20 years for volcanic activity. As we can see, there's a nice white dot, and volcanoes here. There's 4 volcanoes here, and I don't have it plotted on here, but there's a big white dot around 952, a very famous volcano about 20 years after global cooling began. These are years of no summer. Now, let's see where this occurs on our graphic. This is our first 20, 30 years of global cooling, and this is where it occurs on the Lunisolar cycle. The next one, you can see it's pretty much the same point on the cycle. Same point on the cycle. Same point on the cycle. And here we are now. This is what we're heading into. This is my forecast, dramatic global cooling with at least 3 volcanoes coming up before 2030, and one of them very likely being a 7 on the scale, and a high risk of a year of no summer. Back in the year of no summer, in 1815, right here, that was Tambora, a 7. In 1815, that was in Indonesia. In 1816, a year of no summer. New England lost 75% of their corn crop. Killing frost every month of the summer all the way down to Virginia. Ice in small ponds and streams in northern Pennsylvania. That's in the middle of the summer. Europe, potato crop losses. And I believe the estimate was like 1/4 of Europe perished during the next several years through disease, lack of food, and civil unrest. Northern China lost most of their rice crop. And this is what is heading up for us very soon. And there's a gentleman I've been doing some joint talks with. He's John Casey. He wrote the book Cold Sun. He uses sunspots. And they just started a corporation called the International Earthquake and Volcano Prediction Center. What they're doing is monitoring 3 very big volcanic vents around the globe. Any one of the 3 are ready to blow. Any one of the 3 have a potential as being as big as Tambora in 1815. Now, volcanoes aren't usually a huge problem until you put it in conjunction with extreme rapid global cooling. When you get the combination of the 2, you're in for trouble. With that note, I'll end it right here, and we can take questions.
Thank you. Thank you, David. As before, what we're going to do is we're going to put the microphone here, and you can line up and ask questions of David.
David, thanks. I'm Chuck Lear.
Yes, Chuck.
About 5 years ago, the International Panel on Climate Control issued a cautious statement that there was about a 15% probability that global warming was human-caused. Can you comment on that assessment?
They said a 15% chance or a 95?
I think it was 15%.
I think it was 95.
Quite low, as I recall.
I
I'm
didn't hear
incorrect.
that one. What I did hear about 3, 4, 5 years ago was their forecast wasn't really working out for temperatures to continue increasing. Instead, they've leveled off during the past 10 years. So they revised their forecast and said, well, we now see some natural cycles, so what we're going to do is we're going to keep the temperatures steady for the next 10 years and then rapid global warming. What they did was buy time for 10 years. They just recognized the cycle for only 10 years. We're going into a 200-year cycle, not a 10-year cycle. So I didn't hear your forecast. The only forecast I've been hearing is 95% or in that range.
Fascinating presentation.
Thank you.
I'm Bob Wood. You alluded briefly to some work on sunspot correlation. I wonder if you could elaborate on who that is and what he's done.
Well, that was John Casey, author of the book Cold Sun. He used to work for, I believe it was NASA. Many scientists around the world, including NASA, know that we're going to a Maunder minimum in sunspot activity, which means the sun is going to be a little bit colder, which means cooler temperatures, global cooling. Well, he approached the forecast with the sunspot activity. I approached it with the gravitational aspect of it, which would also have interruptions in the electromagnetic field. So although we used a little bit different techniques to get our forecast, we came to the same conclusion. We came to just about almost the exact date of going into global cooling. And I'm not the only one. I've known this since 2007 when I put out my first ebook, but I was afraid to speak up much about it because I was the only one talking about it. So I was quiet when I met up with John Casey this past winter and we did joint talks. Now I'm coming out and talking about the volcanoes and the drastic global cooling that's coming because a lot of people are on the same page.
Rich Ulrey, have you had the opportunity to plot polar reversals in relation to these cycles?
No, I have not. It'd be fascinating to do it. I'd love to do it. If you can get me information, I certainly will. It would take no time at all. I have the model, this model, or what I'm showing you on the cycles. I've spun off many forecast models on this. The El Nino correlates to it. I use it for hurricane forecasting. And just recently, in the past year, I did a model for California earthquakes. I can track the California earthquakes for the past 200 years, right up through my models. And on my website, you could go to my website. I have the California forecast on there free of charge. Go to the earthquake section, my forecast for the big one coming up about a year from this winter. That's the biggest part, the strongest part of the window. We're going into the window now for the strong earthquake, but it's going to be somewhere between December and February of 2013-14.
Could you elucidate a bit more on the dire effects, presumed dire effects of cooling plus earthquake or volcanic eruption?
Well, effects are, first of all, we know we're going to have probably three big, well, you said earthquakes, not volcanoes, right? Volcanoes. We know we're going to have probably three big volcanoes coming up prior to 2030 because we're already monitoring 3 vents that are ready to go. What happens on a volcano when you get a VEI 6 or 7, the volcano injects a lot of sulfur into the upper atmosphere. It's the sulfur that gets up in the upper atmosphere, mixes with water, and makes sulfates. Sulfates is highly reflective. So the incoming solar radiation is reflected back to space. And this is why year 1816, after the volcano, was such a cold year, because of the reflectivity of the solar radiation. And that's what we're looking at. And it's the combination of when you have your first 20 years of global cooling, you're cooling off so rapidly, and you get a jolt with a huge volcano on top of it, and you just jolt it down even more. And I should point out, you can have very strong volcanoes outside of the global cooling, the rapid one, and you don't have the same effects because you don't have the combination. Yes, sir.
My name is Lou Marinkovich. I'm a geologist. And I thought I'd mention that Milankovitch cycles, as you know, are recorded in ocean sediments. And my friends who study modern sedimentation say that the Milankovitch cycle is where it's going into a cooling phase. So it verifies your other data.
Well, we definitely are going into cooling phase. One thing is 7,000 years ago, we were at peak at this interglacial period when we had 50% less ice in the Arctic. That was the peak of a warm period. We're actually starting to cool off towards the next ice age, although that's 40,000 years away. But each global warming cycle will start getting cooler and cooler. And maybe we should pray that carbon dioxide causes warming, because we will need it if that is the case.
Indeed.
And when some of these volcanoes go off, they bump the Earth a little bit. Now, that changes the orbit of the Earth somewhat. And what kind of effect does that have on cycles, if that's true?
I don't know as if it bumps the Earth, which it may, like you said, very slight, it would come right back anyway. But they can probably detect a slight quiver. That would not have a change at all, because any change in the axis would have been very, very, very slight. So we're talking about a 23,000-year cycle where the tilt of the Earth changes from 23.5 degrees down to about 21 degrees, somewhere around there, a 23,000-year cycle. And that's a change of about 3 degrees. And if you get a minor change, it's just a fraction of a hundredth of a degree, it's not going to do a thing. Well, I'm sure it would. I'm sure. I don't have the concrete answer for you on that, but I would have to assume it would.
All right. Thank you very much,
Thank you.
David.